What's up guys, Major Math with another video on fluid mechanics. If you have any questions, drop it in the comments, and if you're having trouble with other problems, I've attached my email in the description, so please feel free to reach out. Without further ado, let's get started. Question 3.123 in the textbook says, this dome, in parentheses, hemisphere is located below the water surface as shown. Determine the magnitude and sign of the force components needed to hold the dome in place and the line of action of the horizontal component of force. Here y1 equals 1 meter and y2 equals 2 meters. Okay, first things first, we might go ahead and redraw this because it looks pretty small. Okay, zoom this out, and then it says from the bottom of the hemisphere, y2 equals 2 meters, y1 equals 1 meter. Okay, so the water, it's water in here, this area is water. Atmospheric pressure, have the height. Okay, it says, so our goal is to find the magnitude of the forces, so the magnitude of the force acting on this this dome, and then it says to, so say find magnitude of force, and then it says to find the line of action for the horizontal. We're given the y1 and y2 heights. It says that the temperature is 10 degrees Celsius. From that we can get the specific weight of water, so therefore specific weight of water equals, go back to the textbook, it says 20 degrees, right? There we go. 20 degrees, specific weight is 9790. You'd think I'd probably memorize those by now. Okay. I think that's all for the givens. Okay, yeah, and a given is that this is a hemisphere also. Okay, so let's try to find the magnitude of force, so the FP. So step one, find the pressure force. When dealing with these curved panels, you have to break it up into the horizontal and vertical components. So let's find the horizontal component first, and we'll label this as FH. So we got this same equation for the pressure force. We're just going to put the FH for horizontal component. It equals, that's not pressure, that's pressure, not density. It equals pressure times density, or pressure times area. You rewrite that as specific weight of water. In this case it's water, just specific weight in general for the formula. And then the height with respect to the centroid times area. Okay, so we can actually start to solve this now. So we already know the specific weight of water. We need to know the height from the surface of the water to the centroid of the hemisphere. And we need to know the area. Okay, so let's find the height first. That's gonna be pretty simple. It's just gonna be this 1 meter plus half of this 2 meter. It's just half because the centroid of the hemisphere is just in the middle, the dead middle. So that's why we're halving it. So I'm not even gonna write that out. I'm just gonna say 2 meters. And then for the area, we gotta think about this for a little bit. So the area, you might be thinking, well, we need to take the area of a hemisphere, but the textbook talks about something called a projected area. So imagine if so we're seeing a cross section right now. If you were to look at this directly, looking at that curve, the area of it, I can't even draw it, but if you were to look at it directly, like that dome, and far enough away, it would just look like a circle, right? So that's where that projected area comes into play. When you're looking at it from the angle where the horizontal force will be applied, so to speak, it's just going to be the area of the circle, which is pi r squared. So we know that the radius would be half, because the diameter is 2 meters, so the radius is just half. So 1 meter, so that the area is just pi meters squared, right? Okay, so we found it. We have all 3 variables. Now we can actually solve for this. Say the horizontal component of the pressure force of pressure, equals the specific weight of water times the height, which is 2 meters, to the centroid, and then the area, just pi. And if you put that in the calculator, you will get 61,638 newtons. Okay, now we have to find the vertical component. That says vertical. We're gonna do V or FV to denote that. So say FV equals the same thing. This time though, we're gonna do something different. So we're thinking about so we have our thinking about these pressure forces acting. These are a horizontal component. We just found that. It's kind of similar to just what you do if it was a slanted panel. But this one's a little bit different. When we never really separated it before with until we work with curved. So now we got to think about this column. I just drew a little column, and we got to think about the vertical, which is sort of just like the weight of the water above it acting onto the curved portion. So to do this, we're going to do, we usually been doing specific weight times height times area. Now we're going to do specific weight times the volume, because we're trying to find that volume of the water, because we're kind of finding that the weight that's being pushed, or the weight of the water that is on top of it is kind of what we're finding. So now we got to do the volume of a hemisphere. So we got to find the volume of the hemisphere and multiply that by the water to find the weight of the water that's on top. So the volume of a hemisphere is is. I put a half here because the textbook gives you the volume of a sphere, so I just halved it because it's a hemisphere. So now we can do, just go ahead and plug what we know in. The radius will just be 1 meter again, like we already have found previously. So that will be times the volume. So 4/6, 2/3 pi, and then 1 meter cubed. Put that in a calculator, you get that the vertical component equals 20,546 newtons. Okay, so we found the vertical and horizontal components, and it's asking it what's the magnitude. So to combine these forces to get the magnitude of the one force acting on it, you just do the vertical component squared. Here, I'll show you. We would just do the vertical component squared plus the horizontal component squared. So, and you add them together. And then if you do that, you will get a magnitude of 64972 newtons. So that is the magnitude of the pressure force acting on that curved surface. Now it wants us to find the horizontal line of action. So we're only dealing with the horizontal. We're going to use that slant distance formula. The horizontal line of action will be on the center of pressure because that's where the horizontal force will act, is right at that center pressure. So finding the slant distance will help us locate where the horizontal line of action is. And that equals the slant distance to the centroid. Don't put a bar over this. So that has nothing to do with the centroid. Okay. Plus moment of inertia, slant distance. Okay. So it's not really a slant distance. So when we break it up in horizontal and vertical, they're at 90-degree angles. So the slant distance is really just the direct height from the surface of water, the water level to the centroid. So it's not really a slant distance. So it's just 1 meter plus half of 2 meters to get to the centroid. So it's just 2 meters. So slant distance, it's not really a slant distance because we broke it up in horizontal and vertical. That's just equal to 2 meters. For the moment of inertia for a circle, and we're using a circle again because at the horizontal perspective, if you were to look at it, it is a circle. The area is a circle from that perspective. So you're going to be using the moment of inertia of a circle, which is pi r to the 4th power over 4. And we know that the radius is just 1 meter. So it's just equal to this. That's just meters to the 4th power. And then our area is just, again, we already kind of found this, pi r, or pi meters squared. So we can go ahead and plug everything we know in. So the center of pressure is located, we gotta plug, if we plugged all these in, we'll just go ahead, these are simple numbers, plug in, found them. If you plugged all these in, you will get 2.125 meters. Again, this is not really the slant distance, that's just the direct 90-degree angle from the surface of the water straight to the centroid. So this is at a depth of 2.125 meters is where the horizontal acts. Thanks for watching, soldiers. Don't forget to leave a like and subscribe for more content like this. If you have any questions, leave it on the comments, and if you need help with any other problems, feel free to contact me with the email shown on the screen.